Gas, pressure, and volume. So we're looking at gases with this new unit, and we're going to be looking at a couple of the gas laws, a couple of new equations that you're going to have to memorize. Okay, and we're going to introduce pretty much one of them, but there are a couple of units that you do need to know, and we're going to cover them in just a second. So, closed system. Closed system is one with a constant amount of moles of a substance. It is not open to the atmosphere. For gases, right, if you contain them within some kind of a container, right, it's a closed system. Right, so however many moles you have is consistent within that container. Okay. Gases in closed systems, from carbon dioxide in fire extinguishers to oxygen and oxygen tanks, perform important functions in our lives. So we've got gases that are in closed systems pretty much all around us. Understanding the behavior of gases in closed system is essential to our safe and effective use of gases. So we know that gases are a state of matter. We go from solid to a liquid to a gas. We know that the kinetic energy, increases as we move from a solid to a liquid, then from a liquid to a gas. Okay. Calculating pressure. Pressure is defined in physical terms as the force exerted on an object per unit of surface area. Okay. So what we have is pretty much the following equation. I ended up taking the attendance anyway. So pressure is equal to force over area. Okay. So units for force, right, that we're going to look at, okay, are newtons. Right? So we'll use newtons. Or use the letter N. Okay. Area, pretty much, centimeters squared, meters squared, millimeters squared, depending on whatever the area of the surface that you're exerting a pressure on. Okay. So commonly used SI units for pressure are the following: pascals, PA, capital PA, is equal to 1 Newton per meter squared. Okay. So these are a couple of constants that you do need to know. And the kilopascal, kPa, okay, which equals to about 1,000 pascals. Okay, so a few things that you do need to know for this unit when we're looking at pressure, because you may be asked to convert certain units, your pascals to kilopascals. You're going to be introduced to a couple of other units later on in this chapter, where we'll be looking at units like atmospheres, torr, but we'll get to those towards the end. Okay. So let's look at the first sample problem. A student with a mass of 51.0 kilograms is sitting on a chair. The force the student applies to the chair is 500.0 newtons. If the surface area of the chair seat is 0.0500 meters squared, what is the pressure the student exerts? But we want them in kilopascals. Okay. So what we want to do, we start off with what we're given, right? And our equation. So pressure, force over area, right? So what of this are we given? Well, we're given the force. Okay. And we're given the area. So that 51.0 kilogram student doesn't play a role in this question. Okay, so be careful with the numbers. Try to isolate what each one pretty much stands for. So let's get rid of that. So we've got 500.0 newtons divided by the actual area, which was in meters per meter squared units. Right? So we divide these two and we get the following: 10,000 newtons per meter squared. Right? But we know that in terms of units, right, we know that 1 Newton per meter squared is equal to 1 Pascal. So if 1 Pascal is equal to 1 Newton per meter squared, What do 10,000 newtons per meter square stand for? One, not kilopascal, 1 Pascal, right? Sorry, so for each one. So 1 times the 10,000 will give me 10,000 pascals. But now we've got this, and we know that 1 Pascal is equal to, sorry, not 1 Pascal, 1 kilopascal is equal to 1,000 pascals, right? So if we've got pascals here, and we want to get rid of pascals, where am I going to put the pascals when we're doing the conversion? Top or bottom? The bottom, right? Because that's where we're going to cancel out. So 1,000 pascals is equivalent to 1 kilopascal. Okay. So pascals cancel out, and I'm left with the right number of significant digits, 10.0 kilopascals. So I multiply this 10,000 pascals by 1 kilopascal, right, which doesn't really change anything, but then we divide it by 1,000 to get us 10.0 kilopascals. So surface area and pressure are inversely proportional. As the surface area decreases, okay, so if the surface area is going to decrease, the pressure will increase, right? Because let's face it, if we've got pressure is equal to force over area. So if the surface area got smaller, right? So we exerted whatever newtons. So we exerted, let's say, 200 newtons at an area of about 10 meters squared. And then we decided to do the same. We were going to exert the same 200 newtons, but the area now is going to get smaller. Right? So the area is going to get smaller. Let's say the area became 2 meters squared. Right? So 200 newtons divided by 2 is going to give me 100 newtons per meter squared. Over here, 200 newtons divided by the 10 meters squared is going to give me 20 newtons per meter squared. So notice now the pressure here, right? The pressure compared to here. Pressure got bigger when the area got smaller. Okay. So notice that the area got smaller, right? We decided to we exerted the same the same pressure, right? The same force. Oops. Ignore when I use pressure for these. Okay, we used the same force of 200 newtons. We divided it by the area, but we changed the area. Okay, this is just a hypothetical question, right? So the area got smaller. As the area got smaller, even if we're exerting the same force, the pressure gets bigger. And that pretty much explains this. So as the surface area and pressure, they're inversely proportionate. When we are talking about inversely, it means that if one increases, the other one decreases. That's inverse. Right? If it's directly proportional, they're both going to go in the same direction. Right? So surface area, if the surface area decreases, the pressure increases, as we see with these two examples. Okay? We exerted the same force of 200 newtons, but the area changed. Pressure of a gas is determined by the kinetic motion of its component molecules. So we've got here a demonstration of a basketball, right? An inflated basketball. So we've got pressure within the basketball, right? The air within the basketball that is exerting a pressure inside towards the outside of the ball. There's also an external pressure, right? An atmospheric pressure that is exerted on the ball as well. Right? So molecules collide against the inside wall of the basketball, giving it its shape. Right? So remember, if there's not as much air in the ball, of course, it's not going to have its proper shape. Right? Each collision exerts a force on the basketball's inner surface area. The collective number of collisions as well as the strength of the force form the net or the overall gas pressure of the actual ball itself. Right? So what's different is, imagine if we we changed, you know, pretty much the ball. We've got it in standard room temperature, but we decided to throw it into a freezer. What do you think is going to happen to that ball? Is it going to burst? It'll deflate. Why? Pardon? Exactly. The particles aren't moving as quickly as they do in the gas, right? So it's going to deflate because the particles are now trying to almost condense itself, right? So the reason why it acts on the inside walls of the basketball here in this example is because the actual, you know, the pressure of the gas within it is pretty much, you know, they're going mental, right? The kinetic motion is very great amongst gases. Right? They're vibrating very quickly, so they're hitting towards the outside. But if we slow them down, that's when you'll start to see that ball start to deflate. Right? So gases pretty much take the shape of their container, right? Which is different from solids, which is sort of different from that of liquids. They do take shape, but it won't, you know, if you don't have it completely filled, right, then it wouldn't take as much shape. And finally, since the molecules move in all directions, the net pressure exerted will be equal throughout. That's why you won't really find one part of the ball less, you know, inflated than the other. Right? It's pretty much the entire ball is somewhat deflated, right? When you check it and you see how well it bounces, right? Is it appropriate to be used to play? Atmospheric pressure, a column of air above 1 meter square at sea level. So imagine 1 meter square pretty much surrounding you. There is a pressure of air that is being exerted on us. The greatest amount of pressure is at sea level. If we went higher in altitude, that's why you're able to hit a ball further, you're able to go, you're able to run faster, because the air is very thin, right? So the atmospheric pressure is lower as you move higher and higher in altitude. Right? So you're able to hit a baseball a lot further. You're able to jump further. You're able to run faster because you don't have the same kind of atmospheric pressure exerted on your body as you do at sea level.
Don't you get like tired?
Right? You do, because the air is also very thin, right? So you got to get climatized to that kind of, to those kind of conditions. I remember when I was in Denver, Colorado, and that's in high altitude, and yeah, you know, the minute, you know, we got off, it was, yeah,
That's when, like,
you know.
when you play like the Rockies, the ball's in like 5 minutes.
Exactly. But you know, and at the beginning, when these teams kind of came in, yeah, there was a huge advantage, right? Because these teams were naturally, you know, training in these facilities, right? Eventually, now with the way things go, you know, it's, you know, it's gotten to a level where it's not making that much of a difference, but it still does, right? Your ability to run in higher altitudes is still gonna, you know, but now, you know, athletes now, you know, are getting to train a little more in these kind of facilities. So, few units to know. Column of air at about, you know, so imagine 1 meter square area around you. At 0 degrees Celsius exerts a pressure of 101,325 pascals. Right? This is equivalent to the following number. And this is the number that you want to know. Okay, so that's in kilopascals. That's the one that if you ever you watch the weather report. Right? They'll be talking about the pressure, and that's the amount of pressure that's exerted at about 1 meter per, you know, 1 meter square of the area at sea level, but at that temperature. Okay. So, as we said before, 1 pascal is equal to 1 Newton per meter squared. This is equivalent to the mass of about 10,000 kilograms over the area of about 1 meter squared. So it's kind of like we almost, you know, like the amount of pressure that's exerted on our bodies, we don't notice it, right? So we don't notice how heavy the air is, right? And even if we did go into high, we really couldn't tell. You know, you'd be walking down the street and you're like, whoa, wow, I'm flying through the streets. No, you're not going to really notice it, right? Because you know, the actual air itself, just the property in terms of its density, right? But if you were in water, right, you're swimming at the top, if you've ever swam to the bottom, right, that's kind of almost like explaining what sea level's like with air and high altitude is with respect to water and being at the bottom of the deep end and how heavy it feels, the pressure, because you've got all that water that is being exerted on your bodies at that time, right? Think of how heavy, right? You feel, you know, the pushing, you know, into your face of the, you know, the water if you've ever swam to the bottom of the deep end, right? Because you've got all that water above you now exerting a pressure on you. As you're going deeper and deeper, that water is getting heavier and heavier. Same thing goes with the air, but we're not going to the deep end with air. Sea level is our base level, and the high altitude is where it becomes lighter. It's kind of like being at the top part of the pool. Okay. So early studies of atmospheric pressure. In the early 17th century, the Italian scientist Galileo Galilei, that's the years he was alive, developed a suction pump. Okay. It used air to lift water up to the surface from about 10 meters underground. When drawn from greater depths, the column of water collapsed before it reached ground level. Galileo concluded that the water could not be pumped higher because it had reached its limit of vacuum. So what we're ultimately getting to is coming to a standard pressure set of units. Right? So what is the pressure that's being exerted? Right? We look at the ball and how there's an atmospheric pressure that's exerted on the outside. There's a pressure that's exerted by the air that's within the ball, right? Giving it its shape. Now, the following scientist, Evangelista Torricelli, continued Galileo's experiments and concluded that the weight of air was pushing down on the rest of the water. So as they're lifting the water, there was really a pressure also exerted by above it. Right? So right now, believe it or not, there is a pressure of air that is being exerted on your bodies. Right? That's not the reason why you're tired, though. Okay? So, but we all do have that. Right? So we've got all this air on a daily basis that is exerting a pressure on us, but we don't really notice it. Right? Because we don't feel like, oh my goodness, I can't keep myself up, you know, for that reason. Right? It's for other reasons. So the weight of air pushed water up the column. There's a diagram in your textbook, a little tubing, shows the water and how the air kind of acts as a pressure. So imagine, let's say, a tubing filled with water. Right? There is still a pressure that air that is exerting on the open ends of the tube to give it, you know, the shape or to give the water where it's positioned at. So this was a logical conclusion since gas molecules, like all matter on Earth, are pulling down on the force of gravity. Right? So remember, gravity plays a very big role. So the same applies with any type of body of water. So you've got the water, and there's a pressure of water that's exerted with the other molecules of water just below it. But there is the atmospheric air, right? The air around us. There is an atmospheric pressure that is also being exerted on that water. Right? So, Torricelli did further calculations involving the weight of the atmosphere by pressing on the water. So here we have this glass tubing. Okay? And so what we had here pretty much, we had a pool of mercury and wanted to see exactly what kind of pressure was being exerted by the atmosphere, right? By the atmosphere around it. He then improved upon the experiment by using mercury, which has a density of 13.6 times greater than that of water. So we thought maybe water was not really the best source or you know the best material to use to go through this experiment. So he used mercury. He designed the apparatus, which we now know as a barometer. So the barometer, right, that's the barometric pressure that the meteorologist will pretty much state what's today's atmospheric pressure. And they'll say, maybe it's 100.3 kilopascals today and rising. Right? So we're looking at what is the pressure that the air is exerting at sea level. So Torricelli filled a glass tube of about 1 centimeter diameter, closed at one end with mercury, and inverted it. Some of the mercury ran out of the tube, but about 760 millimeters of mercury remained in the tube. This number has become very important because this number has become pretty much one of the units used for this pressure. Okay, so the 760 millimeters of mercury. This is about 13.6 times less than the height of the water that Galileo could pump. Okay, so he saw the same results using mercury, but using the density, knowing that the density was exactly the same amount. Right? 13.6 times that. So he noticed that those results pretty much remained consistent. It is the air pushing on the mercury in the dish that keeps this 760 millimeters of mercury in the tube. So what happens here is, just going back, right, with this tube's not rising any further, and so what's happening is the air pressure is being exerted here in this little pool of mercury, and it's rising the level, and it kept it at the same level because there's a pressure on the mercury itself that's pushing the mercury up the tube, and he sealed the top part, so in a vacuum, and it was able to rise by about 760 millimeters. Right, so you'll see this 760 millimeters of Hg, right, mercury, right, the chemical symbol for mercury. So, changes in atmospheric pressure. At first, Torricelli considered his experiment a failure. The height of mercury column did not remain constant at 760 millimeters, but changed slightly as the weather and air temperature changed. So all of a sudden he realized, well, you know, it was 760 millimeters today, and tomorrow it ended up being a little bit less. The day after that, maybe it was a little bit more. So he's thinking, well, maybe that number really wasn't the best number to be used, right? But ultimately it was realized that, well, there are a whole bunch of other factors that play a role, right? Because remember, as temperature increases, right, so do molecules of water. They evaporate more, right? The air can hold more water as a vapor in the summertime when the temperature is warm, right? Because remember, the water molecules evaporate and then fill up the air. But once it becomes saturated, then it cannot hold anymore. And that's when we talk about the stickiness of those really hazy days, right? Those really hot, humid days, right? When we're trying to sweat and we realize we're getting all sticky. It's because the water is trying to evaporate from our body to go into the atmosphere, but the atmosphere is already full of water that it can possibly hold. So, units of pressure. Atmospheric pressure was measured in millimeters of mercury. So, mmHg, the chemical symbol. Standard atmospheric pressure, pressure of atmosphere at sea level and 0 degrees Celsius, is 760 millimeters of Hg, of mercury. So that's the standard. So this is what when we talk about standard atmospheric pressure, we are referring to it at 0 degrees Celsius at 760 millimeters of mercury. Okay, and we're going to put some better units that we're going to use instead of the 760 millimeters of mercury in a second. In honor of the work of Torricelli, standard atmospheric pressure has been defined as 760 torr instead of the 760 millimeters of mercury. So let's put a unit to it. So we decided to put 760 torr. 1 torr represents a column of mercury 1 millimeter in height at 0 degrees Celsius. So we know that for each millimeter, right, we had a total of 760 millimeters of mercury that we formed. But for each millimeter of mercury that's rising, it's equivalent to 1 torr unit. So that torr unit, one of the new units that we'll be using. Another common unit for measuring pressure is the unit called atmospheres, and the short form for atmosphere is ATM, right? Where 1 ATM is equivalent to 760 torr. So let's look at the term called standard atmospheric pressure. So standard atmospheric pressure refers to at 0 degrees Celsius, the temperature, okay, which is equivalent to the following. 760 millimeters of mercury. But we know that each 1 millimeter of mercury is equivalent to 1 torr. So if we have 760 millimeters of mercury, we have 760 torr, right? So notice how we can just get rid of that and just put torr if we want for our units. Right? 760 torr is simplified into 1 atmosphere. 1 atmosphere is equivalent to 101.3 kilopascals, which if we want to go even further, we can convert this to that 101,300 and whatever, but according to this, we'll use just the zeros, pascals. Okay, so using this relationship, we can convert from one unit to another. So we're going to look at a sample problem where we're going to have to make this calculation. So you're going to need to know that. So convert the pressure of 100.0 kilopascals into torr units. Okay. So here's our equation. We've got the 100.0 kilopascals that we're starting off with. Right? We want to get rid of this kilopascal unit. So when we multiply by a fraction, we always want to multiply by something that will allow me to cancel out this unit. So we always put that unit at the bottom, right? Kilopascal. So now what are our units left with? We're left with torr units. But using, you know, that relationship that we showed before, we know that 101.3 kilopascals is equivalent to 760 torr. So we multiply 100 by 760, then we divide it by 100.3, right? And we get 750.2 torr. So that is the equivalent. So all of a sudden, if we were to measure this using the column, right, of mercury, the column of mercury would be about 750.2 millimeters in height. So, relationship between pressure and volume. As external pressure increases, gas molecules are forced closer together. Right? So, imagine a pressure that's being exerted. Right? So, imagine you've got the syringe, right? You just got your needle, you just got your vaccination, and you ask the doctor, can I have the plaster for me? I remember when I used to get my your shots that you need as a kid, I used to always ask for that back. Can I have that and play with it? Fill it up with water or squirt with it, right? So what you do is you seal it, right? And you try to you pull the plunger out and then you push it in while you seal the other end. And you can't push it all the way, right? Because you just sealed the other end. But what you're doing is all the gas that's within that plunger now is trying to get pushed in. If that was filled with a solid, you definitely couldn't move it. If it was filled with a liquid, you couldn't move it. But if you fill it with a gas, you can still move it to a certain extent because all of a sudden now you're compressing all the particles of the gas together. Because remember, the particles of gases are further apart than they are in solids and liquids. Right? So you can always compress them back. So volume of gas will also decrease, right? Because the gas volume is always based on the container that you're holding it in, right? Because you can't measure gas in an open system. You've got to close it into something, right? So as a weather balloon rises in altitude, atmospheric pressure decreases and the volume of the balloon increases. So when they're filling these weather balloons, right, they don't fill them in completely, and as they rise, right, the pressure that's being exerted will also help increase the actual balloon itself, right? So an external pressure increases. It's going to help pretty much bring the particles of gas closer together. Okay. Any reference made about the volume of gas refers to the volume of the container. So if you're measuring gas and you've got, 4 liters of oxygen, it's based on the volume of the tank. you can measure 4 liters of water and put it anywhere else. But a gas, you put a gas that's 4 liters into a container that is 8 liters, all of a sudden now you're giving the gas more space for it to move. Right? So you can compress gas, right? You've seen the symbol, the Wemyss symbol for compressed gas, right? Because the gas, well, you're squeezing a whole bunch together. That's why it's so explosive, because all those particles, they're vibrating so quickly that they want to get out. And the container is what's keeping them in. Right? So, definition of the volume of a gas is the space available for gas molecules to move around it. So, kinetic molecular theory of gases assumes that the volume of each gas molecule is essentially 0 because the amount of space for them to move around is in the volume of the container. So you really can't measure the amount of gas you have until you put it into a container. Because how do you hold it? Like right now, if I try to seal in, now, you know, I close my palms together. And I've got now some air in there. Only if I can measure, I can't measure the gas itself. I can measure the volume that my hand can hold. Right, as I palm my 2 hands together, right, and keep a little opening to allow for air to be in there. Right? That's what's going to be measured as a gas. That's how much gas I have in terms of a volume. Right? So it all depends. The bigger your hand, the smaller your hand, you're going to be able to hold a little bit less. Same thing goes with the container. Right? You're putting oxygen from a 4-liter tank into an 8-liter tank. You're giving it more space to move. So the volume all of a sudden goes from 4 liters to 8 liters because the tank is now 8 liters. Right? So for all gases, the volume of the gas is the volume of the container holding the gas. That's what the volume is for any type of gas. So whenever we are referring to volume of a gas, we're always referring to it as the volume that is being held within that container. So the container is 4 liters. You're holding 4 liters of gas. Whether it's full or not. Right? You order those helium tanks, and you're down to just enough helium to blow maybe 5 more balloons. However big that tank is, that's how much gas you really are holding. You're still holding the same volume of gas from the time you bought the tank to the time you finish using the tank, because that's how much you can possibly hold. Boyle's Law. Robert Boyle, Irish scientist who investigated the relationship between pressure and volume of gases at constant temperatures. So, key thing in Boyle's experiments were that he looked at pressure and volume of gases, but he made sure that the temperature remained constant. So these are 2 sets of measurements that are going to play a very big role when dealing with Boyle's Law. Now, he stated that the volume of a given amount of gas at a constant temperature varies inversely with the applied pressure. Right? We've looked at the term inversely, right? Meaning that if one's going to go up, right? If we're going to increase one of the measurements, the other one is going to go down. Okay? So as an external pressure of a gas increases, the volumes, okay, so here we've got an external pressure that's going to increase, right? It's going to go up. But the volume of that gas is actually going to decrease, right? So there's that inverse proportional. Okay. So we're looking at how one goes up, the other one goes down. If one goes down, the other one is going to go up. That's what we're dealing with inverse proportions. So this is known as Boyle's Law. So here's an animation of Boyle's Law. So what we're doing here, we've got this plunger and we've got these masses here that are in the middle that are exerting a pressure on the gas within. Right? Notice how the gas particles are getting closer and closer together. So as the pressure is increasing in this direction, notice what's happening with the volume. The volume is decreasing in this animation. Right? So the volume is going here from the top, here from about 4, let's say, liters or whatever. Notice here the pressure is continuously increasing. So as the pressure increases, the volume decreases. Why? Because the particles of gas are getting closer and closer together. They're compacting within one another. And that's something you couldn't do with a liquid. You couldn't do with a solid. All right. So notice here, what's the same? Temperature. Temperature doesn't change. We're keeping the temperature the same, right? Constant temperature. But pressure, we were increasing. What happened when the pressure increased? The volume decreased. So Boyle found that this relationship held true for all gases as long as the temperature remained unchanged, right? That temperature being constant is what we said was very important. So what we have here in this diagram is, well, we've got the gas, right, within the container. We're exerting a pressure, right? An external pressure is exerted with the gas, and notice how, well, the gas is still pushing up at this plunger, let's say, that is trying to push down, but the particles, look at how much space, how spaced apart they are from one another, right? Look at how spaced apart, and they're getting a lot closer, so the amount of space in between is getting smaller and smaller. So as we're exerting a pressure, right, pressure is increasing, this volume is decreasing. So as external pressure on a gas increases, volume of the gas decreases. Okay, the gas molecules are forced closer together, hence the less amount of space. But if we're talking about the volume of this gas, right, we're looking at it in terms of how, how much space. So even though we said, yeah, you know what, the volume. So what is the volume here? Let's say the volume here was, I don't know, 2 liters. The volume here has to be less, still 1 liter, right? Because remember, we're basing it from this plunger being up here as opposed to being down here. So the amount of space that we're given is a lot less. So as the pressure of a closed system increases, the volume decreases. If the pressure is decreased by half, the volume doubles, right? So it's inversely proportionate, right? So if it increases by 3 times, it will decrease, the other will decrease by 1/3, right? So if the pressure decreased by half, so we're lowering the pressure by half, the volume is going to increase inversely. So we just kind of flip these 2 over and we get that, right? So if we're decreasing something by half, the volume is going to increase. So this relationship mathematically is shown by using the proportionality symbol alpha. We use a little letter called alpha here to show the following. So here is that inverse proportional. We've got the volume is inversely proportional. Right? So if it's inversely, right, we're inversing. Right? It's not V is proportionate to P, which means if this increase, this is going to increase. But this does not hold true, because what happens is if the volume increase, the pressure has to decrease, and we show it as this 1 over P as a fraction. Okay, so the equation above means that the volume is inversely proportional to the pressure. Let's get rid of that symbol, and we put it as V is equal to 1 over P. Okay, so it pretty much, means the same, right? We're going to add a constant to it. So what is that proportionality constant? So that constant is the fact that the temperature remains constant. So what we want to do is we want to keep P, and we want to actually move it over to this side of the equation, because, well, whatever that constant is going to be, that temperature that's ultimately going to remain the same. So our conditions that are remaining the same. And we get the following equation. K is equal to P times V. Okay, and we're going to see a little bit more about this as we pretty much expand on Boyle's law. The following. So for a gas sample at its initial conditions, we're going to use the letter I. Right? So if we've got the constant, proportionality constant, we've got our pressure and volume, but we've got it at its initial state. So we're going to label it with a subscript I, just to show the difference between one pressure to another. Because what we're going to do is we're going to change the gas from one, exerting one type of pressure, and we might change it to exert a different type of pressure and try to find the volume using that. Right? So if the gas sample is then subjected to some kind of change, right? So we might change the pressure, we might change the volume, right? So we want to find out how has it affected the other, right? So we're going to denote it with the letter F. So we're going to have the same condition, same constant, sorry, and we're still going to multiply our pressure by volume, but now it's the final pressure that's being exerted multiplied by the final volume, right? And we're going to ultimately put together the following. Now, since the slope of the line K is constant, and since initial and final conditions are both equal to K, we can write the following. Okay, so the initial pressure and volume is equal to the final pressure and volume. So we want to see what change has been made, right? What's constant? Temperature is not changed, right? So this mathematical relationship is another way of stating Boyle's law. So when we're talking about Boyle's law and you're asked to answer a question using Boyle's law, or you're given pressure and volume, this is the equation that you need to know. Okay, we'll talk a little bit more about the slope later on. Okay, so let's look at this first sample problem. A sample of helium gas is collected at room temperature in a 4.50 liter balloon at standard atmospheric pressure. Okay, so standard atmospheric pressure. The balloon is then submerged in a tub of water, also at room temperature, such that the external pressure is increased to 110.2 kilopascals. What will the final volume of the balloon become? So, take a moment and just isolate the values. What information are you given in this question? And then set up a set of givens and work from there and see what you need to find. And what is it that we need to find? We need to find the final volume of the balloon, right? So we're trying to find the VF. That's really what we're trying to find. So you should have the following givens. The initial pressure, 101.3 kilopascals. Now, we don't have this unit in the question. Where is this number? Some people are going to be asking. Well, the thing is, we said standard atmospheric pressure. When we refer to standard atmospheric pressure, we are referring to 101.3 kilopascals. Our volume, initial volume, 4.50 liters. Right? The helium gas collected in that kind of a container. We've got the final pressure, which is where the pressure actually increases. We want to figure out the volume, right? We want to find out the volume of the actual balloon. What will the final volume? And that's really our VF, as we said. So, looking at the information that we're given, right? We've got the initial pressure and volume, initial pressure only, so we need to find the actual final volume. So, here's the equation that we're given. And what we want to do is, we want to isolate for VF. So, take a moment and complete the following problem. Now, so what I like to do for these kind of questions is I like to substitute my numbers first. So, what's my initial pressure? Well, my initial pressure is 101.3 kilopascals. And I like to use the units, keep the units going. Right? I'm going to multiply it by my initial volume, which is 4.50 liters, equals my final pressure has gone up to 110.2 kilopascals, and I'm multiplying it by, we could label it as V2 if we want, but I've been using VF for this example. So what we're going to do eventually is I'm actually going to simplify this part. So I'm going to multiply those two together, and I'm going to get 455.85. And now we're going to use a set of units that really don't exist, but we're going to use it because, well, we're multiplying a kilopascal by a liter. So we're going to have kilopascal multiplied, we're going to use a dot, by the liter. Right? That's simplified the left side of the equal sign. On the right side, we have 110.2 kilopascals multiplied by the final volume. Now, what I like to do then here, I want to isolate for my final volume. So I divide this side by 110.2 kilopascals, right, which will cancel those out, and I'm left with just my final volume, right? What I do there, I must do also on this side. So I divide this side by 110.2 kilopascals, and my final volume is equal to 4.13659873, and kilopascals here cancel out. I'm left with just liters, so my answer is in liters. But based on the least number of significant digits in my question, which is 3 sets of significant digits, so we want the 4, the 1, and the 3. We look at the 6, that 6 bumps that 3 up. So the answer, our final volume, is equal to 4.14 liters. And that is the final volume of the balloon.